Hello everybody and welcome. Today we're going to be taking a final example on energy transformations, and it is the conservation of energy inside a vertical spring. Now, let's look at the types of energy that this spring will be dealing with while it's moving up and down. First of all, since it's moving, there will be kinetic energy. Sure, at some points it will be zero, especially when it's at its lowest point, and at its highest point it won't be moving anymore. The kinetic energy in this case will be zero, but in general there is kinetic energy. There's elastic energy because the spring is being stretched and compressed. And finally, there's gravitational potential energy because the spring is going up and down. So let's go more into detail. Now, the mechanical energy at any moment is going to be the addition of the potential energy that is elastic and the potential energy that is gravitational and the kinetic energy. So at any moment we can find the energy of the object by adding all these forms of energy. But that doesn't mean that all of these forms must be present at the same time. So let's start with this spring when it's at location A. Like the green line is the rest length of the spring where it's not stretched or compressed, and the red line is the floor. Let's imagine that the red line is the floor. Now, I will compress the spring from its original length of x1. So I compressed it by a distance equal to x1, and now it is at a height, let's call it h, above the ground. So let's study what types of energy do I have. The spring is pushed, gaining elastic potential energy and gravitational potential energy. So the spring is not moving because we did not let it go anymore, and it won't have any kinetic energy. So the mechanical energy at location A will be the elastic potential energy plus the gravitational potential energy. Okay, now let's say that we let it go at location B and we took a picture when it went back to its original length, which we said it's the green line. So now it's not either stretched or compressed. So the spring is now at its original length. Since it's moving, it will have kinetic energy. It will not have any elastic energy because it's not either stretched or compressed. It will have gravitational potential energy because it's still above the ground, and this time it will have kinetic energy because it is moving. So we can say that the energy this time is mg multiplied by half the height plus half mv squared. Finally, let's say that the spring is going to continue to move, right? At a certain point, it will reach its maximum stretched length. It will stretch to a length beyond its original length because, it has kinetic energy and potential energy, and it still tends to move. At this moment, the object is very close to the ground, so it won't have any gravitational potential energy. The object is not moving because it will stop and start going in the other direction, so it won't have any kinetic energy. So the only form of energy here is going to be the elastic potential energy. So quickly the spring is stretched again at a distance x. The spring's velocity is now zero, therefore there is no kinetic energy. The height above the ground is zero, therefore there is no gravitational potential energy. So things are coming more clear right now. We are learning how energy is transforming from one shape to another. There are mainly three important questions. Is the object moving? Is it above the ground? Is it a spring that is stretched or compressed? Ask yourself these three questions. If it's moving, we have kinetic energy. If it's above the ground, we have potential energy. And if we have a spring that is stretched or compressed, then we have elastic potential energy. So let's take a quick example. It says here, if a spring had a mass of 0.5 kilograms and the spring's constant was 20 newtons per meter. Find the total energy at point A, knowing that x is equal to 0.5 and h is equal to 1 meter. So if I want to quickly draft it right here, this is my spring. It has been compressed at a distance equal to 0.5. So let's say that this is the original length. This is my spring, and it has been compressed a distance equal to 0.5 meters. And this is the ground, and it's 1 meter above the ground. Can I calculate the total energy in this object? Sure I can, because we know at this moment we have two types of energy. We have potential energy that is elastic, and we have potential energy that is gravitational. Can we calculate them? Yes, easily. This will be the total energy here. The mechanical energy is going to be equal to the gravitational potential energy plus the elastic energy. So we're going to say that the total mechanical energy is equal to mgh plus half kx squared, and everything is given. So the mass is 0.5, g is 9.8, and the height above the ground is equal to 1 plus half multiplied by the spring's constant, which is equal to 20, and multiplied by the distance it was stretched, which is 0.5 squared. This will give us a total energy of 7.4 joules. So the total energy is 7.4 joules. And remember that this energy will be conserved through the whole journey. Part number 2, find the velocity of the spring at point B. Point B was when the spring reached its original length. So if we want to sketch it quickly here, now it's at its original length. This is the dashed line which shows the original length, and it is above the ground at a distance. This time it will be h over 2, which is equal to 0.5 meters. So if I want to calculate the energy, I will say that the energy or the mechanical energy at location B is going to be equal to the kinetic energy plus the potential energy because it's above the ground. Does it have any elastic potential energy? No, because the spring is neither stretched or compressed. I know the mechanical energy at B because it's equal to the mechanical energy at location A. So I can substitute it 7.4, which is equal to the kinetic energy. I know that the kinetic energy is equal to half mv squared plus the potential energy, which is mgh. And I will start substituting numbers. 7.4 is equal to half multiplied by the mass, which is 0.5, multiplied by the velocity, which is unknown, and we want it, v squared, plus the mass, 0.5, multiplied by 9.8, multiplied by the height, which in this case is 0.5. So 7.4 is equal to 0.25 v squared plus 2.45. If we multiply all these numbers together, we will get a 2.45. So I will subtract 2.45 from both sides. Now I will have that 4.94 is equal to 0.25 v squared. So I will divide both sides by 0.25, and I will get that v squared is equal to 19.7. And since I want v not v squared, I will take square root for both sides. Then I will get that v is equal to 4.43 meters per second. Okay, so it's pretty easy and straightforward. For the third question, it wants us to find the distance the spring will stretch to at location C, which is after it loses all its potential energy. What will happen if we can draw a quick sketch? This is at location C. Now, it's on the ground or closest to the ground, and this is the original stretching height. It's asking me how much did it stretch beyond this point. Well, we know at this point right here, we won't have any kinetic energy. We won't have any gravitational potential energy. We will only have elastic energy. So let's say the mechanical energy at C is equal to PE elastic. Now, I can say that the total mechanical energy is 7.4 because we already found that. This is equal to half multiplied by k, which is 20, multiplied by the stretch distance x squared. Now, 7.4 is equal to 10x squared. I will divide both sides by 10, and I will get that x squared is equal to 0.74. But since I want x, I will take square root of both sides, and I will get that x is equal to 0.86 meters. In other words, if the object is 1 meter above the ground and this point is the midpoint between the ground and the distance it was compressed, the distance remaining between the ground and the stretch distance is 0.5 meters, but it's going to stretch a distance equal to 0.86 meters. In other words, it will hit the ground before reaching its full extension. Okay? I hope things are more clear right now. Stay tuned for some more examples and problems on energy transformations that will make everything clear. It's very important that you solve them, and stay tuned.